Current 2024. Nile, take one.
LinkedIn, take one.
Pinterest, take one.
Bloomberg, take one.
Can you please introduce yourself and tell us where you work?
Yes, I'm Gwen Shapira. I'm a co-founder of Nile.
My name is Vahid Hashemian, and I am a software engineer and tech lead at Pinterest.
My name is Sumedh Sakdev. I'm a senior staff software engineer at LinkedIn.
I'm Madhuri Jain, and I'm a senior software engineer at Bloomberg.
So what sort of things are you working on at Bloomberg?
I specifically deal with derivatives market data.
My team manages the PubSub platform at Pinterest.
I'm a creator of Open House. It's an open source control plane for managing Apache Iceberg tables.
We're building serverless Postgres for modern software as a service applications.
Can you tell us a little bit more about sort of the motivations behind the company?
You know, databases haven't changed in 40 years, but the kind of applications that we're building changed a lot. Why are databases staying the same?
Our long-term mission has been to provide our users with a reliable and efficient planet-scale PubSub platform.
Our low latency derivatives data streaming pipelines that I built are designed to keep up with this ever increasing flow of data.
And a lot of it is really driven by our users. They need it to be more scalable, they need it to be faster, they need new ways of processing data.
One thing this kind of a technology enables to not think about storage layouts, rather they can continue to focus on their streaming applications and the high throughput ingestion of their data.
What does that mean for the people who are actually working with these streams of data?
I myself worked on stream ingestion pipelines, and I see Open House as an enabler for data streaming engineers.
We especially have seen a great shift toward the streaming applications, and because of that, we do call ourselves as data streaming engineers.
So would you say that you're a data streaming engineer?
Of course, I'm a data streaming engineer.
In a way, you can say that we're seeing the rise of data streaming engineers.
Vice President, Developer Relations for Confluent, Tim Berglund.
Good morning. It is good to be back. Good morning and welcome to day 2 of Current. You made it past day 1. That's outstanding. And with that video in your mind, I have a question for you. And I'm going to need phones out. You should have phones out anyway. It's good to take pictures of conference, right? Tweet them. Anyway, please scan that QR code. Please visit the underlying Slido poll. And I would like if we could switch to the results and we could see these in real time. What would you say you do here? What do you call yourself? What is your job? And look at, I don't think this is powered by data streaming technologies. Look at these results flowing in real time. I'm excited. Okay, all right, there's a few of you. This actually is very interesting. Maybe we need to be in touch with the folks at Slido. There you go. Okay, so some results flowing in there. We scroll up and down. Organic cauliflower farmer is getting a better showing than I expected. A lot of software engineer, a lot of software architect. There's a lot of words. You're thinking of, we as technical people, me and the people who write stuff. A lot of words we use to describe what we do. Jay started, if you remember yesterday morning, he gave a little bit of history, right? I want to do that same thing, slightly different, going to zoom out a little bit, but this idea of being a data streaming engineer, I want to look back through history and the way I see this story. Work with me, about 5 minutes here. I think this is an important story that sheds light on what we're doing here. So back to, away from the poll results, a lot of software architects, a lot of organic cauliflower farmers in the room. That is a surprise. Okay, 1951. The year is 1951. It is the dawn of commercial digital computing. The first commercial mainframes are coming online. Big, expensive batch analytics machines, okay? We sort of fret about the operational analytical divide now. Wasn't a thing there. There was no operational data. It was just analytics data, just batch data. And if you did this back then, what were you called? You were called a computer programmer. There was no such thing as a database administrator. There were just tapes and punch cards. Eventually, this operational analytical divide started to emerge. It's a thing that had to come online. You have 10, 15 years later, terminals becoming a commonplace thing. So you can actually, this thing that we understand, we type at computers, that was a thing that had to develop. And with that, you had actual databases in the way we understand them, sort of in the way we understand them, coming online in the mid-60s, and the idea of capturing a transaction and recording it in a computer became a thing. You were still probably a computer programmer, maybe a data analyst. That started to kind of become a thing as data started to shape up. Well, for 30 years, this mainframe paradigm ruled like dinosaurs, ruled the earth until, and I'm picking these dates, this is my history, we can argue about the dates later, but 1981, the IBM PC is released. It's not the first microcomputer by any stretch of the imagination, but now computers are showing up on desktops, and there's a paradigm shift. Instead of folks like developers and architects in this room writing software for mainframes, now we're writing software for these super fancy client computers, and you know, they're doing things on desktops, and it's great. Where does the data go? This is a tremendously disruptive paradigm shift in the way business software is written. The data now isn't in one central mainframe database, but it's in 100 little databases in little computers, maybe made by this guy, shout out to Texas here, right? On computers stuffed under desks and in closets, and databases proliferate all over the place. Huge disruption in the way applications are written, huge disruption in the way data is managed. The idea of there being a data warehouse is born because of this revolution in computing. And it had a name. It was called client server. Now, if you were, let's just say for a random example, a nerdy teenager in the late 80s reading, say, Byte magazine, I've maybe heard a story about a guy who was like this. You know, people were writing about this client server thing like it was utopia. It was going to change the world. It was crazy, right? The equivalent of me back then was really making a big deal out of this. And it was a big deal. It did change the way software was written. The web happened just a few short years later, and that changed a lot socially. It was a hugely disruptive thing. Interestingly, didn't really change the way enterprise software got written all that much. Instead of saying, you know, Visual Basic in 1992, now it was with a terrible early stage web browser, but the underlying architecture, if you were there, I'm looking around the room, and I know some of you were, we didn't say client server, we said 3-tier, but it was the same thing. That paradigm, that starting in 1981, that client server paradigm, the web happened, it didn't care, didn't notice a thing. You still had the legacy data warehouse, you still had essentially the same architecture, until now, in the late 2000s, smartphones. This is what broke the dam. Now there was too much data. Now our commercial and social lives are increasingly going to be mediated through these devices that we carry. That's really happening kind of 2008 and later. And that now we're seeing cracks in that client-server paradigm. Now, all of a sudden, the legacy data warehouse architecture can't quite cut the mustard anymore, and we're starting to see new ideas. So, broadly speaking, dividing up the history of digital computing into these eras, we've got the mainframe era from 51 to 81, and then from 81 to, I'm going to say 2011, because those are both 30 years, and I like the way that fits. You've got this client-server era. In 2011, that's not when Kafka was created. It is when it was open-sourced, so it makes the dates line up nicely. 51, 81, 2011. You've got mainframe, you've got client-server, and now the era of data streaming. If you were, again, back in those client-server days, writing application software, what'd you call yourself? A computer programmer. With the proliferation of databases in the client-server era, maybe you called yourself a database administrator, maybe a sysadmin. That kind of became a term that came into use. And now, in this era of data streaming, we've got lots and lots of things we call each other, call ourselves. And when these revolutions happen, when there is this big sea change in the way software architecture works, lots of ideas, lots of companies, lots of concepts get explored. Back in the day, and you can go and read archived, I keep picking on Byte magazine, go read archived Byte magazines, look through the ads. You'll see companies that don't exist anymore, some that do. You'll see ideas that are now footnotes, they're now Wikipedia pages. You'll see ideas that lasted. There's a lot of exploration and a lot of creation and some mistakes that get made at these pivot points. Why am I talking about the pivot points? Well, we are all data streaming engineers now is not just a slogan. What I am trying to say is that what's happening right now that we are talking about, we are here at Current exploring, that many of you in this room are actually building, this has only actually happened once before in the history of digital computing. When the mainframe era gave way to what I'm calling the client-server era, that was a period of disruption and innovation and whole new technologies, whole new little sub-industries. That's happening again now. Look at the problems we're solving, right? I mean, when the monolith died, when we kind of decided client-server was a bad idea and we started using a mean name to describe it, and we said, okay, let's build our systems with microservices. Well, I mean, that was kind of terrible for a little bit, right? Until we really discovered that Kafka was the right way to do that. And when we became the recipients of the massive flow of data that, frankly, mobile devices were responsible for, that, again, really gave a context and a place where Kafka could come into existence and really be adopted the way it was. And when you've got all that data in those topics all of a sudden, what are the odds that it's just in exactly the right form that you want it and you can just dump it into your data lakehouse and analyze it and it looks great? Well, that's just not how it works. That's why you have a thing like Flink comes into existence. What about the old systems, okay? When PCs came on the scene, mainframes did not melt into a puddle and drain into the drain. They're still running. The code that was running in 1980, a lot of it is probably still running now, and those now are legacy systems that we have to integrate with. Well, that's why we have things like Kafka Connect and the whole integration story. And once we've got all of these disparate systems, again, if you think of the chaotic diagram that Jay showed yesterday morning, all those things integrated, you need to govern that data. These are the things that show up and that are a part that define the lives of data streaming engineers. Now, that legacy data warehouse that is now the cloud data lakehouse, that's not going anywhere. This streaming world needs a way of a story with which it integrates into that whole thing, and that's the TableFlow story that we've got here. So this isn't a slogan. We are all data streaming engineers now. It's a recognition that the reality of our world has changed. The way we build systems now, the way we will continue to build them, I think for decades to come, is changing, and we're getting an idea what that looks like. What I want to spend the rest of our time on, what we are going to spend the rest of our time on this morning, is a survey of what's going on in the space. So I've mentioned these technologies. We've got Kafka, we've got Flink, we've got Iceberg and TableFlow, we've got governance. These are the things that, if you're a data streaming engineer, you need to have a grasp of these. So we're going to cover what's going on in these spaces, show you what's been happening in the last year, what to look forward to. You will be, I think, better equipped to think of yourself. I'll come back in a little bit with some more thoughts. For now, we're going to get started with Kafka. I'm going to welcome Anna Povsner and Senda Jacobs to the stage. Thanks.
Good morning, Current. It is great to be with you, and thanks, Tim, for that intro, that little stroll down memory lane history lesson, reminding me of all my favorite mainframe migration projects. Anna, if we're going to get started with this talk about the rise of the data streaming engineer, there's only one logical starting point, and that is the streams themselves. Now, if you're in this room, joining us online, that takes us straight to Apache Kafka. And Anna and I are here to catch all of you guys up on the current events in that space. See what I did there? It's early, I know, it's early. Apache Kafka is the de facto platform for event streaming, full stop. And these numbers speak to the work of this community to grow the platform. You see Kafka's popularity all around the data streaming space, even in the Kafka alternatives. After all, imitation is the greatest form of flattery.
And Kafka continues to mature, becoming the trusted utility that is always there. Like walking into a room and flipping a light switch or turning a stove in your kitchen, it's there. You expect it to just work. And this trust is reflected in the Kafka user base. We're talking about the 10 biggest names in manufacturing, IT services, and insurance, 8 of the 10 largest telecom companies, 7 of the 10 biggest names in retail and banking. When companies are looking for a trusted event streaming platform, more often than not, they turn to Apache Kafka.
That's right, Anna, and those are great points. And Kafka's all of these things. But progress and improvement are priority number one in this community. Just look at the most recent features in the latest releases, like tiered storage or queues or the next generation consumer group protocol.
And how about Keep 390? So until now, only the default compression levels were used for each codec. And now you can tune compression to your needs. As always, with any tuning of configuration, you need to consider trade-offs. In this case, it's CPU utilization to compress your data and I/O to store the compressed data. So we always encourage you to test, and retest. Maturity also includes reducing the total cost of ownership with features like craft. So good things are happening in recent and upcoming releases. But more than that, there have been some recent changes that makes me, as a developer, that much more excited to use Kafka. And you should be excited too.
Quick question, Anna. How do you feel about containerization?
I think we're all fans here, right? I think it's a good thing.
Seems like a friendly audience, and Kafka and Docker are good friends. In fact, many of the people sitting in this room are the innovators and experts with containerized Kafka. But there hasn't been a Docker image released by this community until now.
And now, like other popular Apache projects, Keep 975 publishes an Apache Kafka Docker image using the ASF Docker profile. So going forward, every release of Apache Kafka will publish a new Docker image, including release candidates. This will also include example Docker Compose files and quick starts. Since Kafka is already being built and tested with Java 21, the Docker image supports Java 21 as well.
That collective sigh we heard, both in here and online, that's the Java 8 people in the room. Sorry, guys. We love you anyway.
Continuous containerization. Keep 1028 introduces the Docker official image for Apache Kafka.
Yeah. Anna, didn't we just talk about that on the last slide?
Sort of, but not really. Keep 1028 builds on Keep 975 to introduce Docker official image, reviewed by Docker. Other Apache projects like Flink, Spark, and Solar have Docker official images with 50 million to over 1 billion downloads. So there is a demand. These official images are considered more secure than sponsored images due to their more strict and transparent build processes. For example, regular security audits, updates, and signature validation. And this is especially important to Kafka users in highly regulated verticals, such as banking, healthcare, insurance. And having these images available is great not only for running Kafka in production, but also for testing.
Speaking of testing, Anna, wouldn't it be great if that test lifecycle was just a little faster? There's a KIP for that, and that is KIP 974, which introduces Graal VM-based Docker images for Kafka. These Kafka native images run in craft mode by default, totally keeperless, and Test Containers supports this as of version 1.20.1 of the Kafka module. We've got good news and we've got bad news. Here's the good news. As you can see on the screen, we've got a set of test suite that's running here, one with Kafka native and one with what I dubbed Kafka Classic. Kafka native runs that suite 4 times faster than Kafka Classic. There's always trade-offs and side effects. The bad news is that warm cup of coffee won't last through your CI/CD builds anymore. You won't have time to refresh it. So, but seriously, Anna, in a suite of like dozens or hundreds of tests in your CI/CD pipeline, this could make a real difference.
Yes, and that is great. But let's talk about insights. People writing Kafka clients are not Kafka operators. They may not be aware how their clients and configuration impact the cluster and other clients. And this can be a real problem, especially in large clusters. Be a good citizen, a responsible citizen, but we do need insights to find those raw clients. Keep 714 provides a mechanism to send Kafka client metrics to Kafka for use for monitoring and troubleshooting. It defines 2 types of metrics: standard, what the client should report, and required, what the client must report.
In Kafka Streams, we see this great example of this community coming together and coalescing around a problem. to improve the platform for all of us, like uncaught exceptions in a topology that stop the world and terminate processing, unless you get those little try-catch statements just right. And that's tedious and error-prone, right? KIP 1093 proposes a new mechanism for handling those exceptions. And then building on that, in KIP 1034, we implement DLQ routing for Kafka Streams topologies. With a configuration parameter, you can route those problematic messages to a DLQ, including the metadata about the error, like the exception, the stack trace, the topic, the partition, the offset. And this is included in the 3.9 release already. So Anna, tell us a little bit about the new happenings with Kafka Connect.
Okay, Kafka Connect. So first of all, if you ever needed to make a minor update to a connector configuration, you know it can be both frustrating and error-prone. KIP 477 provides a patch endpoint to the connector configure_est API, making this pointed update so much more simple.
Yeah, so you're telling me that with Kafka Connect, I don't have this git, edit, put, and pray lifecycle anymore when I'm updating configs?
Exactly.
Yeah. If you ever fat finger the config, this is for you.
So, Sandon, you've made those changes. And your connector is still somehow able to scale beyond the task max value that you just provided. Turns out that setting was more of a suggestion to some connectors in the previous Kafka releases. KIP 1004 adds configuration to enforce the task max setting. As of now, it's defaults to true, is deprecated, and is slated to be removed in an upcoming major Kafka release.
So what's next for Kafka? Kafka's next step is turning the big 4.0. But Tim already promised me there's no budget for black balloons and tacky decorations. Maybe a tacky cake or two, but we'll see. But what you can expect are more and more impactful feature updates that you, the data streaming engineer, will want to incorporate into your data streaming pipelines. Because ultimately, this community of developers and users make this technology successful. And with that in mind, to introduce you to new tooling for data streaming engineers using Apache Kafka, we would like to welcome Matthew Seal to the stage for a demo.
Thanks for the warm welcome. Today I'd like to talk about a new abstraction for working with Kafka and Confluent resources. Specifically, we're going to be talking about, could we go back one slide? No, we're good. Specifically, we're going to be talking about a VS Code extension, which provides visibility and tooling into your streaming development. And as of today, this VS Code extension is available on VS Code on the marketplace, as well as GitHub. So we've open sourced this and kind of put it out here in space so all of you can see and interact with this code base. Thank you. And we're still early days in this extension, but we wanted to put this out when we had something that was really stable and a great skeleton for building upon. And we'd love to get your feedback and input on where this could go to really enable your ability to build good streaming applications. Now, why did we build this thing? Well, this really starts with what we wanted for ourselves when we came into the streaming world. When I first started switching over from Batch and some of my teammates switched from application build or ETL systems, you land and streaming looks almost the same, but there's a lot of subtleties and a lot of tooling changes you really have to dig into and understand. And this really makes it feel like you've landed in the deep end of the pool sometimes. We have to go dig through documentation, and you're not quite sure how things behave. So we really wanted to address the ability, especially for newcomers to the space, to really get an understanding of what's my data look like, what are the things I have access to, how does this thing work, is it doing what I expect? And these pain points really drove us to thinking about what will be a good experience. And we saw there was a big gap. There's no good Kafka tooling in VS Code. There's some in some other tools, but even there, it's not as much as you would like. So we wanted to dive in and really tackle these pain points and give a good basis for understanding what's happening in a streaming application. So let's dive into it and see what the code looks like. So you can see here, we're in VS Code. And we've got this extension installed. You can just go ahead today and go onto the marketplace, search for Confluent or Kafka. This will pop up. So you install it. You can see there's a walkthrough here. We're going to basically show Hey, you can log into your Confluent account, you can play with your local CLI for local clusters, and it has guidance on some of the capabilities and features that are in here to use. See here, you can't quite see it off the side of the screen, but you've got this login, so you can manage what account you're logged into Confluent Cloud. We've also got some local topics. We'll come back to those and talk about what we're going to do with them. Now, if I look over here on the left, I've got this resources panel. This lets me dive into an environment and look at a particular cluster. Here, we've got some data that one of our engineers has built. This is their Spotify data put onto a stream in Kafka. You see we have a few topics, some with schema, some without, some iteration of joining these with different data that may have been developed. And you can see here we can go ahead and play the messages. We were just looking at the schema involved with one of those. If you dig in, now we have this message viewer. So right from the IDE, I can see, hey, what are the messages that are in this topic? I can zoom in on one of these, expand and see the fields and kind of understand quickly what's happening. Maybe I want to find another message like this one that has the same artist. So I can go ahead and search for that across the stream. And this will basically go find the rows and the kind of histogram of data up there. I can filter this further by brushing. And then I can go ahead and say, hey, I found another row that looks like this one. Maybe I want to just see how they differ. So you can use the built-in VS Code capabilities to select and compare. And immediately we've got white space diffing on two messages. We didn't have to do any work here. We can already see what's different between these two. Really helpful if you're searching through and trying to find a poison pill or just understand how something changed over time. And here, we've got additional searches and capabilities of filtering and partitioning and other things. We can also do the same sort of behavior with schemas. So here we have two different schemas and two topics that were used, or we could use two iterations in the same topic. And this gives us another, again, white space visibility into what changed in the schema or what might be different. Quickly see an iteration cycle without having to leave your editor. And then one last kind of major component we have in this, we have the ability to do these bootstraps. So one of the things we talked about, getting started being really difficult. Here we have a few fields. We're going to fill these out. If you put in real values and you click generate from here, this will create a Kafka Streams application. We've got a bunch of other templates in there as well. And right away, this is going to work immediately. So with real values, you can run this, and you can get started with a functioning template that has a real application. You don't understand how to set this up and how to get your build.gradle, things like that. You can just immediately get started and understand, hey, what's happening, and start looking at what's flowing through your topic and do minor changes as you gradually learn what all the pieces are. Here we've built a project, so this pops us out, and we made a new workspace out of this. It's got a nice configs property, got a build.gradle, got a readme about how this thing works, and gitignore already set up. And you can see we expand in here, and here's our Kafka Streams application. Nice and simple, just a short little Java program. This could be any language. There's already requests to make this exact template, but in Scala. And yeah, we can see on the left, we still have the same resources. We can go look at our topics. We can do inspection just like we were before, and we're logged in. And we still have the walkthrough and all the other sidecars. Now, there's additional templates here. We have like a half dozen in this example. We're adding more all the time. But it's really get you started on different things, even including the new tables API that you heard about here at the conference. We have a template for that to get you started. And yeah, we also have the ability to give feedback and report issues directly from the IDE, just basically making it really pleasant to be able to step through and understand what's happening. Now, thank you. So we'd like to have you come develop with us. This is open source. You can scan the code here to jump to the marketplace and see, and come see what we want to be building here. We have a lot of the roadmap items in there. We're adding more all the time. And we'd love, if you are a customer of Confluent, to get connected with us, join our EA program, and really help set direction on the major things we'll be building. Thank you, and I'd like to welcome Lucia Sershi.
Let's talk about programming languages. There might not be a topic that we as developers love to debate more than the inherent flaws and merits of different programming languages. However, when it comes to making the final choice of a language for a project, that final choice is often determined by external pressures, like, do the developers on the team know the language? Does the language gel with the languages already present in the project? Now, there are Kafka clients and tools in more than 20 different languages. So, no matter what language you choose, or you're stuck with, you're likely to be able to work with it in Kafka. And this is due, in large part, to the Kafka client community. Let's give it up for them. Today, I am super excited to announce that Confluent has released a new JavaScript client. This client is in early access, and it will be in limited availability imminently, very soon. This client stands on the shoulders of giants. Let's go back one. So it is based on Node-RT Kafka. It has an idiomatic interface similar to that in Kafka.js. And like a few other clients, it currently uses libRT Kafka based off the main branch. So I thought, why not have a little fun with it? NoSQL or SQL, tabs or spaces, Kafka streams or Flink. As software developers, we know that the true answer to any of these questions is it depends again, and it depends a little more. But here's a full stack app to answer these questions using the new JavaScript client. It's a poll that updates in real time. So let's have a little fun, vote now, and settle these debates. The votes behind this website are stored in a Kafka topic in Confluent Cloud. The JavaScript client produces and consumes from the topic in order to update the latest statistics. Now, we collaborated with the client community to make it completely convertible from code that uses Node-RT Kafka. So let's say when I was building this application that I used code from Node-RT Kafka, and I wanted to migrate to Confluent's new JavaScript client. I would change this line, and my migration is complete. Now let's say in my consumer, I used code that's convertible from Kafka.js. In order to make that migration, I would change that import line. I would make sure there's a Kafka.js object in the top level part of the configuration. And then I would need to be aware of a few changes in the admin client, error handling, and schema registry. But again, that's not a huge pull request that you're going to be reviewing to make that migration. Now, once I run these files with Node.js, I can verify that my messages are coming in with the Confluent VS Code extension without leaving my editor. So I invite you to play around. I was in the audience yesterday. I've seen a few pull request reviews happening. So if you've got your laptop out, npm install today. Now, I would love to welcome to the stage David Anderson and Danica Fine.
All right. Good morning, everyone. We got good music. This has been great. Yeah. So now that we are all caught up on everything relating to data streaming as a whole, I'd say it's time to move on to the next phase of our journey where we think about using those real-time streams of data, right? So if you're a data streaming engineer, and let's face it, we all are, you know how difficult it can be to stand up a brand new application, whether that's an end-to-end pipeline, a new dashboard, or whatever else it is you're building. But rarely is it the case that we have exactly the right data lying around in a Kafka topic with exactly the right schema. And even if you were so lucky for that to be the case, I'll bet you still need to do something with that data. Enrich it with another data set, aggregate it, filter it, before it's in the format you need for your particular application. So you need a technology, whether that's a framework or a library, that's purpose-built with your event-driven architecture in mind. You need stream processing.
Now, there will never be just one solution for stream processing, but it's clear by now that Apache Flink has emerged as the choice of the community, and for plenty of good reasons. Flink just ticks all the boxes for what you're looking for in a stream processor. Above all else, it just works. It scales, it's fault-tolerant, and it's got the flexibility that data streaming engineers are looking for. It offers layered APIs, that you can program to using the language of your choice. And of course, Flink is a stream processor, but it's also a very capable batch processor, supporting ad hoc analytics as well.
As a stream processing framework, Flink just makes sense. You see proof of that in the ever-growing number of use cases out there using Flink, and the companies out there that are trusting it with their mission-critical workflows. And if that doesn't convince you, you might take a look at some of the other impressive numbers around Flink. Over the years, nearly 500 Flink improvement proposals have been suggested, with work being completed by a thriving community led by a talented PMC of over 50 members and over 100 committers. Plus, Flink plays well with everyone's favorite streaming technology, Kafka. And I think that's part of the reason why Flink is going to remain popular and remain the choice of the community for stream processing.
Well, sure. And speaking to the integration between Kafka and Flink, with Kafka 4.0, Kafka will support the two-phase commit updates that Flink so desires. And, well, it's not just about Kafka. It's also Java. Flink has been keeping up with the latest advancements in Java and now supports Java 17 and Java 21.
But most importantly, the open source Flink community is listening to data streaming engineers like you. It's delivering new features that you want and need. And ultimately, this means that Flink as a technology is constantly evolving. It's becoming richer, easier to use, and more developer-friendly.
Danica, I need to let you in on a little secret.
What's that?
If you want to make something simpler, start with something really complicated.
I think this is the only man who can make that claim. We'll talk about that later. But actually, if you look at the improvements being made to Flink over the last 6 months or a year, it's obviously making things easier for you, for data streaming engineers.
Well, yes, very much so. I think one of the biggest ways in which Flink is becoming easier is, well, the improvements in Flink SQL.
Yeah.
So in the past, you may have found that Flink SQL was almost the perfect use for one of your applications. But you didn't choose it because it was missing one small feature or another that you felt you just had to have. If that's been the case, it's time to take another look. With recent releases, Flink SQL has become much more configurable, adding support for fine-grained control over things like watermarking, state retention, Kafka partitioning, and so on. These improvements, I think, are even overshadowed by improvements in the API in general that have made Flink SQL more powerful and easier to use. And I'm thinking particularly of the improvements to the windowing API. A new approach based on table-valued functions has been rolling out over the past 4 years and has finally come to full flower. And you can now use this without reservation. And it supports seamless interoperability with the rest of what you might be doing. Things like deduplication and joins now work very nicely with windowing. So all of this adds up to Flink SQL becoming more powerful and more expressive. And for most real use cases, it's clearly the right place to start.
Yeah. Now, data streaming engineers aren't just those of you writing Flink applications. You're also operating Flink. And we've made your lives easier, too. So ask yourself, what's one of the biggest challenges for operating your Flink jobs today? I'll bet it has something to do with understanding what's going on within those jobs, right? So a huge win for Flink operators these days comes in the form of improved observability. So there are a few pillars of observability, right? We have logs, metrics, and traces, and we need all of those in the right place and the right time in order to understand what's going on within our Flink applications. A number of flips have come about recently to expand on observability and give you the very best view into your Flink applications as possible. For example, as of Flink 1.19, Flip 3.8.4 introduces a new trace reporter interface. Building on that, Flip 3.8.5 will introduce a brand new integration with OpenTelemetry, and that's huge for those of you using that project. Also building on Flip 3.8.4 is Flip 3.8.6, which gives us better visibility into what happens during that recovery process with the ability to add and report on custom metrics. On top of that, we have Flip 3.7.5, which offers a built-in cross-platform Java profiler, so you can dive in when you need to. But beyond observability, operators will also see faster recovery times with Flip 4.4.4. So prior to this update, during recovery, state had to be re-downloaded with manual bytes copying using input and output streams. And with this change, you'll see support for native file copying. So again, that process will be a lot faster. Now, I'm missing something. What else is there, David?
Well, how about something that addresses the struggle between the data streaming engineers developing the applications and the operators hosting the infrastructure that runs those applications?
A tale as old as time. Tell me more, David.
Well, no one enjoys playing the blame game. Unfortunately, Flink jobs can fail. And when they do, we need to figure out who to blame. Well, no. We need to tell who to inform about it. Is this a problem in user code that they should fix, or is this a problem for the operator to deal with? And should Flink automatically try to restart the job, or will it have to be resubmitted? So Flip 304, which was introduced as part of Flink version 1.18, solves this by introducing pluggable failure enrichers. This makes it straightforward to classify exceptions and to annotate them with additional helpful information. So now we know who to notify about each specific error and whether or not Flink needs to try to restart the job. For example, you might be a developer and your job uses a specific Kafka cluster to access a topic that you're going to join with, and you forgot to get yourself permission to access that cluster, and so the job fails. Well, now we can tell you what went wrong, how to fix it, and automatically restart the job once you've done so. On the other hand, maybe your job throws an invalid cast exception. There you're going to have to fix your code, and we'll expect you to resubmit the job.
What about something like system errors?
Ooh, yeah. There are things like network timeouts that developers don't really want to hear about. Sure, it's a problem, but we expect the operator to deal with that on their own.
Yeah, so this is great. It sounds like we can finally avoid spamming users and operators about problems they can't actually solve. So ultimately, this will save everyone some time. So as you can see, data streaming engineers have a lot to be excited about in Flink these days. And while all the features we talked about are either already available or just on the horizon, you have even more to look forward to in the very near future with Flink 2.0. So Flink 2.0, this is a little bit more of a spring cleaning type of release. That might sound boring, but I promise this is great because you clean up the old, you have more room for the new. So in the next major release, you can expect some cleanup and a simplification of a lot of APIs. You'll see the removal of the Scala APIs as well. And in addition, excuse me, in addition, we'll be getting rid of some features that apply to batch only. Now, that doesn't mean you still can't do batch processing in Flink. It just means that we're leaning further into this idea of unified batch and streaming and making sure that all features apply equally to both. So again, even though we're doing a bit of cleanup in this release, there are still some cool features to look forward to, right?
Oh, very much so. One new feature I think is quite interesting is an experimental new state backend that's coming as a beta preview in Flink 2.0, and this is known as the disaggregated state backend. Now that's a bit of a mouthful, but let's explain what's going on. So with the current approach to state management, Flink keeps the local state, the working state, locally on each compute node on the local disk, and relies on periodic checkpoints to a distributed file system to make everything robust. This has worked extremely well for the community over many years, but by now we are reaching the point where some Flink jobs have huge amounts of state, and this can make recovery rather painful because these enormous checkpoints now have to be downloaded to the local disks before we can restart from a failed job.
But wait a second, David. We just talked about Flip 444 and how that recovery process is a lot faster. So how is this different?
Well, sure, we've made the recovery process faster, but there's nothing like not having to do it at all.
Oh, cool.
So the idea here, the big idea, is to unify the working state with the checkpoint state and keep all of that in the remote file system. This is a really cool idea. It's a bit complicated. It's going to take some time for this to really impact everyone. If you're using the Data Stream API, you will probably have to make some code changes to your job to take advantage of a new asynchronous execution model that is being worked on for this. On the other hand, if you're using Flink SQL or the table API, the community can just make those improvements to the runtime on your behalf, and you'll be none the wiser, except things will work better.
Nice. Well, that's pretty cool. So if you want to check out the new disaggregated state backend or any of the other new features as part of Flink 2.0, you're in luck, because there's a preview release coming by the end of this month. Okay, that's in the next 2 weeks, so keep your eye out. Now, David, I know we haven't talked about it yet, but a lot of work has been done in Flink to better integrate it with machine learning and AI. So what do you say? Should we show something off?
Yeah, let's do it.
All right. So, David, I know you came out on stage today to talk about Flink, but I have a proposal for you.
Okay.
You now own an e-commerce storefront specializing in pet supplies. How does that sound?
Wow.
He loves it. He loves it. This is your future, David. So let's say that as a responsible storefront owner, you want to automate the process of responding to negative product reviews so you can make things right for your customers in real time.
Sure.
And I don't know, why not toss in some cutting edge AI just to make it fun, and specifically agentic RAG? That sounds fun, right?
Oh boy, well, okay, RAG, I've heard of that.
Yeah.
That's this retrieval augmented generation. And agentic is some made up marketing word. What is that?
You know, the thing about made up words is that eventually they're real. Okay, so this is what we're going to do, and this is how I envision this system coming together. So it's a real-time system, right? And I think we can all agree that the backbone of any real-time system has to be Apache Kafka. So at every stage here, you'll see data flowing through Kafka topics. Beginning on the left, we have our product reviews coming in from our customers. This is flowing in as just unstructured text. And then from there, we'll use the new AI model inference that's built into Flink SQL on Confluent Cloud to set up AI agents that will then process and make sense of these reviews.
Well, I'll accept that Kafka plays a crucial role here, but I'm going to tell you that Flink SQL is the backbone here.
That's fair. Okay. Equally weighted.
It's the integration framework that's going to pull everything together and make everything happen.
Yeah, so let's actually see it happen. All right, so we are going to kick things off here in Confluent Cloud, where we're going to take a look at the product reviews that are flowing in from our customers. Now, we take a look at these. You can see here's one from Snowball's owner saying that Snowball hates the smell of these salmon-flavored treats.
Well, poor Snowball.
I know.
So I guess we're going to have to implement some agents to extract information from this review.
Exactly. So to do this, again, we're using AI model inference that's built into Confluent Cloud. And from the Flink SQL workspace, we can actually poke around and see some of the models that we've already defined, like one that predicts whether a review was written by a bot. And we can describe this model and see that it's a remote model served by OpenAI. It's backed by the GPT-4o LLM, and it's a classification model, right? It's going to determine whether a review was written by a bot or a human. And in a similar way, the other models are going to solve their specific tasks. So you might ask yourself, how do we actually call these models? Well, it's pretty simple. It's as easy as this. Here we're populating a new topic called NLP product reviews, and we're just selecting values, one from each agent subtask.
Right. So in addition to the agent that does the bot detection, we also need one to predict the rating. We need one to extract any products that have been mentioned in the review. And finally, we want to understand the cause of the rating or the sentiment that was expressed.
Right, exactly. And so we're calling each of these models using the mlpredict table function. Okay. And so here is how our results will look. So we're specifically filtering for that salmon-hating bichon frise, aka Snowball. And so here we can see that the sentiment is 1 out of 5. It's likely not written by a bot. It's about those salmon-flavored treats. And the sentiment reason is a very strongly worded smell hatred.
Well, that worked well, right? But I think now we need to write some code.
Yeah, but before we actually write code, I want to show you some of the order history data set that we're going to be pulling in to augment this. The order history lives in a MongoDB Atlas instance. We have a CDC source connector constantly pulling inserts and updates in real time. And this is important, okay? We're in this situation, we are grounding our data with additional information about the customer. We don't just have that one negative review, we potentially have an entire history of orders from this customer. And for the case of Snowball, this means that their owner in the past purchased beef liver treats. So now we can write some code and respond to our customers, David. And for the sake of time, we're just going to implement one branch of this decision tree. We're going to focus on human reviews from human reviewers who left negative reviews. Okay? So first notice here on line 6 that we're filtering down the reviews to just the negative ones whose sentiment is 1 or 2 out of 5, and specifically those that were written by a human. When we pass this filter, then we're going to go join on the Mongo data set that we have.
Right, so this finally is RAG.
Yes, this is RAG, David. All right, so now that we have all of this rich context, we have our past orders, we can then create one final AI agent that can make a better product recommendation for us. Then from there, we can go ahead and prompt the model, both with the bad review as well as that extra product context we have, and ask for a recommendation. So for Snowball, this will say something like, all right, the customer didn't like those salmon-flavored treats before due to smell, but in the past they bought and liked beef liver treats. So let's poke around and see what the result of this model is. And so here we'll select from our results topic, and we're filtering for Snowball, and we'll see that Snowball here is being recommended a chicken liver treat.
Well, that's great. At least it's not the salmon that lacked the, what was it, the liver aroma that she loves?
Exactly.
But I'm curious, what if we hadn't grounded this in the past order history?
That's a good question. So we can actually run this model without that additional data from those past orders, and we will see, when this runs, we'll see that Snowball is being recommended in this case, just a chicken-flavored treat. And like you said, that lacks that liver aroma that Snowball so clearly prefers. So I think this works. And the last step in the system is a microservice that then ships this recommendation back off to the customer. Now, this could be an in-app message or a notification, or maybe an email that we ship to the customer saying something like, sorry, Snowball wasn't happy. Here are some chicken liver treats on us. What do you think?
Well, you know, I wasn't that thrilled about running a pet food store. Sorry.
But you're a natural.
Well, when you let me use Kafka and Flink as part of running this store, that made it a lot more fun for me. So I enjoyed seeing how we can use these technologies to pull AI together and make things happen with it. This is great. And now that we've brought all of us up to speed on what's new in the land of stream processing, it's time to welcome Adi Pollack to the stage, who's going to take us on the next step of our journey towards analytics.
All right, thank you.
I am so excited to be with you all here today. And today we're going to talk about analytics. Yes, analytics. I know it's kind of a weird topic in a data streaming event. But before we get started, please scan this barcode and let us know where you all standing on a continuum from 1 to 5 in your data streaming journey. Are you just learning about data streaming? Are you starting to use Kafka for 1 or 2 things? Has Kafka become pervasive and impacted the way you build your applications? Or are you also doing significant stream processing? And how about, has streaming has already impacted the way you do analytics as well? Wow, cool results. A lot of love for Kafka, doing significant stream processing. See some folks already starting to use Kafka for 1 or 2 things. Very exciting results. Well, fantastic. This is the right time to be here and talk about all the good things. Well, once data streaming starts to pervade the way we're building systems, you might realize that there are endless possibilities to improve the overall work of our entire data infrastructure. For example, if we take a look at the analytical estate, we have multi-hop architecture. This is the backbone for every time that we work with batch data. Multi-hop architecture means that every hop inside my architecture is actually a batch job. It can do things like transformation, adding schema, cleaning the data. And oftentimes, what starts as a simple data pipeline grows and grows into multiple data pipelines that do similar yet slightly different things. And pretty fast, this architecture becomes a monolithic end-to-end point of connections. And this is where the challenges are actually rising. So this is the time to understand what are these challenges and how we can fix them today. Multi-hop architecture was built for higher latency. This is by design. Oftentimes, what we do is we're trying to create a micro-batching that kind of simulate the feeling of streaming for our customers to improve our customers' experience. So we're building things like 5 hops of 5 managed intervals, and then we get the result in 75 minutes, for example. Well, this works. If we need to go back and change some things, we need to wait for another 75 minutes. Yet, we didn't account for actual failures. And while our systems are pretty durable, there is still overhead that enters into that space. So we need to think about how we're spinning up and tearing down all this amount of jobs. So a quick back-of-the-envelope calculation means that if I have 1 5-minute macro-batch interval, it would accumulate to 105,000 jobs a year. And this is a very simplistic approach. Usually, we don't have just 1 batch job. We're looking into something like 10,000, 40,000, and so on, which accumulates to more than 1 billion jobs a year. This is very expensive in terms of spinning up and tearing down. And that's not all. We suffer from null values. Things can be expensive. Things can get brittle. We see things like dedupe that we need to do later on in the process. And it makes everything that we do with analytics very, very hard, because our goal is to unlock the insights from the data warehouse and the data lake, yet all of these things that just happen to us because of the system accounting, we need to make sure we're building them to account to all loose ends. This is why sometimes it feels like our analytics side is burning. There's a lot of overflowing demands and many, many moving parts. You can imagine, for example, how in the world of the new Gen AI and machine learning, our analytics system also needs to support historic data for that and have multiple versions of that historic data. So what can we do? As data streaming engineers, we have multiple responsibilities, some of them related to the data quality, some of them related to the smooth handover of data between the different estates. After all, we're building data in motion, right? Well, in order to fix the problem, let's go back to basics. Multi-hop architecture is optimized to do infrequent updates, and it is predicated on tables. So what's available in the table world, in the open source specifically? We know things like Apache Iceberg, Apache Hudi, Apache Pymon, Delta Lake. These are all open sources that were built to support tables. They are inherently tabular structured storage that supports ACID guarantees. Iceberg specifically was developed by Netflix to mitigate some of the consistency and partitioning challenges around the data warehouse. What's nice about Iceberg that it's supported by some of the most popular processing engines in the world. For example, Flink, Trino, Presto, Spark, and even SaaS solutions like AWS Athena, Snowflake, and Databricks. So how can we solve the problem? How can we handle the data cleaning and structure at the source so my table can actually be in good shape for the get-go? And perhaps you've heard about a solution like stream table duality. Does that sound familiar? Yes, this is TableFlow. This TableFlow solution is built on the concept of stream-to-table duality. It takes data from my stream and turns it into a table. In practical words, it syncs data from my Kafka brokers into an Apache Iceberg in append mode. It also takes care of compaction. And for the people who do analytics, compaction means we can now say goodbye to our initial small file syndrome and the slowness of compute. Now, this is not all. We only solved one feature of the problem, but we need to have a bigger solution that can actually drive us towards the future. We want to change our infrastructure in a way that we are set for success with all the changes and everything coming our way. This is where data evolution and consistency really plays an important part. This is the time to think big. We want data evolution, we want consistency, we want quality, we want to be able to set ourselves into a good state in the future with generative AI and machine learning. And we know that in order to do that, we need to solve the problems at the source, because otherwise we'll just create multiple yet similar data pipelines. So how do we make it all go away? Perhaps something like upstream data guardrails can be a solution for us. But how? We want to get practical. I'm happy to share that Schema Registry enables us to do just that. We can reduce faulty data downstream by enforcing quality checks controls upstream. For example, Schema Registry enables me to do validate on the producer side, meaning during my Kafka serialization phase, the data is already being validated for me, so everyone on the consumer side can benefit from a clean, healthy data. If there is a failure and something does not comply with my specific expression, for example, you can see here null values. I don't want to have any null values in my data. I can decide on failure to send it into a deal queue, or I can fire an alert, or I can send an email. So I have different solutions that I can start building, and I can start building them right now. The second thing that I can do is actually on the consumer side. We can define transform rules. And transform rules enables me to take the data and change it according to some specific rules that I built in advance. For example, I want to capture the full name of a person. I know something happened in my schema, and I want to make sure that I have the right value in the right place. If I didn't get the value for the full name, I'm going to populate it out of existing information that I already have. This is an example of how data schema transform my data. So what does it mean for different topic migrations? This actually enables me to simplify everything related to topic migrations, because now I can move from having that correlation point in the middle and the consumer needs to actually take care of the different versions into a seamless experience using these migration rules that I just created. And if that sounds a little bit familiar to you, you might think about things like schema evolutions and different solutions like that. This is exactly it. This enables me to build schema evolution at the source so I can already manage all the different versions that I have and making sure I'm building that quality guardrails, that evolution guardrails, this validation guardrails right into my source. All right. And we can't really talk about technology without actually seeing it, right? So how do we shift left to make it right? I want to welcome you for a second back to our AI-driven pet store. As you've seen before, our real-time AI system works flawlessly. We have the great agents. It works just in time. It has the context that we need. And we are recommending treats to Snowball, right, based on existing and previous reviews. Now, finance team put some call in my calendar and reached out with some notes saying that, you know what, we actually have some discrepancies in our data. We have two different reports. One is saying that we are profitable, and the other saying that we're losing money. I definitely hope profitable is the one, but we do need to be more serious about how we're solving this thing. So what you're going to see is two things. One is you're going to see TableFlow and how I'm using TableFlow, and I'm connecting my Iceberg tables together with my Snowflake Polaris catalog. And the second thing, and how I go back to the topic, and actually create that quality rules to fix the bad data at the source. So later on, when everything gets populated and gets sent downstream in my Snowflake environment, everything is already clean and good to go. So here I'm back in my VS Code. You've seen it before. We have the great VS Code Confluent plugin where I can take a look at my data and see what exists in there. And in order to start using TableFlow, all I have to do is to ask that my cluster will be TableFlow enabled, meaning every Kafka topics that I have there are going to automatically be TableFlow enabled. So here I am back in my Snowflake environment. And in my Snowflake environment, I already defined some of the volumes that I need in order to start running Iceberg. What's interesting is I can actually take a look at my catalog integration. So let's run this query, and let's make it big. And you can see here that the information is connected to the catalog source through Iceberg REST. It has a catalog namespace. It has a table format of Iceberg as expected, REST configuration, REST authentication. This catalog URI is calling back to where I saved all the metadata through my TableFlow experience. Perfect. I have, because we're looking into dynamic pricing, we're fully running on machine learning. So I have this topic named dynamic price data. I want to create this new table now so I can actually start exploring what happened in my data. Now again, this comes from my topic. You can see this in the external volume. It attached to my catalog, and I just created that data. Fantastic. Let's run a quick limit 5 to just see what exists there. All right, I have offset timestamp keys, user ID. I have this guy named Franz. Seems familiar. Someone told me he's a Kafka expert. Chicken treats, dynamic pricing. Ooh, I have a negative value here in dynamic pricing. Does that mean that funds actually benefited a little bit out of us? Let's check. Let me run another SQL query where I can actually summarize by the dynamic price, where dynamic price is below or equal to 0. All right, I can see all this potentially bad data or potentially faulty operations that happen in my stream. I see friends definitely benefited, Dibdiman and Dave as well. Okay, let's fix that. Let's go back to my Kafka consumer and add a quality rule. In order to do that, I want to implement rule executor. Rule executor is part of my schema registry library right in there. And I'm implementing this new interface. This interface has two functions that I need to override. One is CEL, Common Expression Language. This is the type of what this operation is going to have inherently. And the second one is transform. Transform, here I'm using Boolean. I'm calling check dynamic pricing. And check dynamic pricing returns a Boolean true or false based on if dynamic price is bigger than 0 or false if it's equal or lower than 0. This is what I need to do. Second thing is I want to actually connect it. So I'm going to create a new topic that's going to have this data quality rules attached to it. And the only thing I need to do in order to so my system will know it exists, is to configure my producer. These two lines are going to tell my producer that now it has to comply with very specific quality rules around dynamic pricing. You can see here I'm giving it the class in reflection. Lastly, I want to create this new JSON file with the rule set because I want to tell my schema registry what to do on failures. And on failures, I'm giving it the deal queue, so that means I'm already going to get a new topic on when this expression doesn't comply. The data is going to be sent into my dynamic price data deal queue. Fantastic. Let's start running it. And let's start looking at what exists. You can already see here I have my deal queue that was created automatically. And data I started to pull in because there are a couple of bad datas into my system. But this is all good because now what I have, I splitted my topic. I have my deal queue one, and I have the topic with the high quality. Potentially. Let's take a look. Go back to Snowflake and see how it looks like. So here I'm creating a new table, DQ dynamic price data, that pulls the information from my new updated topic with the data quality rules. Creating the table, letting Snowflake do its thing. And I'm going to run the same query that I ran before, only now with the new updated topic with the data quality rules. Lo and behold, I get nothing. I don't know if that means that it worked or that means that there's a glitch. So let's go back and run some limit 5 on it just in case, just to make sure there's real things in there. Yes, the numbers look right, and I just accomplished my mission. I shifted left to make it right. Thank you. With that, I'm pleased to bring back to stage Tim Berglund.
To start to tie all this back together, started by asking you what you call yourself, and I'd love to know the real answer. We could talk about that later. And I don't know if my, very brief 10-minute summary of the history of computing, if that's like a new thing you still need to think about. If you've got thoughts, you should post them on LinkedIn, #current24, tag me. But here's I think a much more important question. So you just listened to, let's think back to what we just heard. We heard about Kafka, we heard about Flink, we heard about new and more official and more complete and responsible JavaScript support, new developer tooling, shout out for that. And you just saw Adi tie all of that together with table flow and this idea of shifting left, which is a fairly new emerging architectural idea in this world of data streaming. So the question for you, remembering all that, is what were you thinking when we covered those things? Were you thinking, yeah, no, I'm doing that. Were you thinking, oh, I'm not doing that, but I'd like to. I feel like I should. You know, that kind of software developer shame, like, ooh, we're not doing the right thing yet. You know the feeling. Or I haven't thought of that. That's exciting. The question isn't really, you know, my framing or our claims about this, but if these things are landing and these sound like the things you're doing or you want to do, well, you may in fact be a data streaming engineer. Something for you to think about as you leave in a few minutes. But first, this is not a thing done alone. This is a thing done as a community, and we get to do now for the third time, third year in a row, the Data Streaming Awards. And this is a community-driven, industry-wide awards program. There's an open nomination process. Hopefully you were aware of that. We'll publicize that process again in the next year when we do this again. And the nominations are voted on by this industry panel. You may know some of these names. I certainly count some of these people as very good friends from companies and places all over the world. So it's this broad process, these great people who vote. And I am happy to give the award to these three companies. Solent Tech, this is IoT meets the farm. So there are devices and all kinds of real-time data. They're aggregating field-level data. Get it? Field level. Tough crowd. I thought that was fun. All right, you know, fine. Field-level data to kind of digitize farm operations and do real-time analytics over that and provide actionable insights to grow food, which is a thing I think we all like. Netflix, maybe you've heard of them. Of course, they build a lot of sophisticated things on top of Kafka and Flink to deal with all of their real-time data that they've got. And finally, Conviva. Conviva has partnered with a nameless, large streaming media provider to provide streaming exclusive NFL games. And again, they're gathering quality of experience data from the streams, doing real-time computation so people can watch football and American football and do it with better quality. So these three folks, we thank them. Congratulations to them. They, by the way, anybody, a hand if you're with one of these companies. I would love to see a hand. I can't see because the lights, but you know your hand is there. I see you back there and there. Awesome. At 4 p.m. today in the Meetup Hub, we will present representatives, each of these three companies, with the mechanical keyboard of data streaming. Yes. Round of applause. You're going to want the award next year. Maybe it won't be a mechanical keyboard again, but it'll be cool. All right. A little bit of housekeeping before I send you away. I did a search this morning for streaming selfie, the hashtag, and you know, I saw some. I'd like to see more. Please take a selfie with your friends. Find me, take a selfie with me. I don't care who you take a selfie with. I think it helps. Publish, post it, LinkedIn, Twitter, Mastodon, whatever you want to do. Current24 is your hashtag. The program committee, these folks also need a round of applause. Do you even know? This is a big event. There are a lot of submissions. These folks plow through them all. Huge thank you to them. The code of conduct, encourage you to be familiar with that. It is not complex. Summarized by be respectful, be kind, and have fun. It's available in the app. And as you know, the sessions you don't go to, those are being recorded. You'll be able to get them. And our sponsors, visit them on the expo floor. They're a part of what makes this possible. So a thank you to them as well. Now, I am, in a minute, about to walk out that door because I have a job to do. And I guess you can stay here in your seat if you want. But it doesn't matter what you built. Doesn't matter what you've called yourself. You walk out that door, you are a data streaming engineer. Get to it.